Welcome to another episode 26 of Bayesian Cognitive Modeling Live, where I learn how to do Bayesian inference, along with the practice exercises within Bayesian Cognitive Modeling, a practice course. Today, we are going to be finishing up chapter on the generalized context model, which we spoke about yesterday. I think we're going to extend it in order to infer latent groupings from characteristics within the data. Neat, fun. It's going to be a good day. If you're new here, check out all the other episodes. However, do note that it's really just me sort of doing a think aloud through the exercises. So understandably, it wouldn't imagine someone would want to sit through, well, now I guess it's over 24 hours of content. But yeah, pick and choose around. There might be something useful. I imagine the introductory stuff that I talked about in the beginning might be useful. Or if you're looking to just see me work through some of the more practical examples, I also do that later on. So go ahead and check it out. And pardon the quality of my stream sometimes, because apparently the CPU bandwidth might have dropped some frames on some of the streams, and I might not have been aware of that because I wasn't monitoring the stream. So there's that. However, we're here for it, either or. So we're just going to get right into it. I'm going to pull up the chapter, and we're going to do a little refresher on the process model we're looking at. We're looking at memory right now. Specifically, we're looking at categorization, how people categorize things, and how there might be differences in underlying strategies for categorizing things in terms of the weighting that they place towards various features associated with stimuli. And if only I could, talk and find the book. Here's the book. And whoop-bang. Let's respect that we've gone through this much of the book. All of this. That's right. All of this. Coming up where we are. Whoopsh. We're going to be doing the third section today, which is going to be talking about these latent groups. And if you remember, we initially started talking about the, identifying latent mixtures in the, mixture chapter. I believe it's chapter 6. So latent mixture models. We discussed various ways that we could predict people's countries they were from, advanced exam scores, what have you, whether they were cheating on a test or a psychological assessment or neuropsychological assessment, etc. And now we're going to put that technique or method that we learned in prior chapters to good use by incorporating it into the larger model that also accounts for individual differences. So let's get right into it. And, we might start heuristic decision making today. We have a couple more days here, depending on how quickly we move through the last two examples. I want to make sure I have sufficient amount of content, and I don't want to start a new book or something before I run out of stream days. And here we are. Okay. Latent groups. Piece of paper. And chapter. Over here. This will probably be the biggest graphical model we've looked at. So that's cool. So we've gotten to the stage where we really can start decomposing each of the particular pieces of the graphical model. I'll just leave that on screen for you to peruse while I prep myself here. I'm just going to read up here. Okay. So last time we expanded our generalized context model in order to incorporate individual differences on a generalization parameter, the weighting of the stimuli parameter, as well as the baseline probability between the choosing category A or B. And in most cases, this was 0.5, or we set it to 0.5, but we also went ahead and changed the stand code and showed how you could infer this value, and it ended up being like 0.49, pretty spot on. So now, one interesting I want to say pattern, right, that we notice in the joint posterior distribution between weights and the generalization was that we had these potentially distinct clusters of how individuals classified the stimuli, with indicating 3 having one pattern of responses, 33 having another pattern of responses, and then 31 being quite all over the place. And in fact, if I'm not mistaken, 31 sort of represented this not understanding not really understanding the task, which in itself is a category and would be useful and interesting if we could identify subjects who seem to not understand the task instructions and didn't, or we could infer that it's possible, or it's possible that they did not understand the instructions given the pattern of categorizations that these subjects here in the low generalization, middle attentional weight between the two features in the stimuli. Here is being height and length position, line position and height of box. To remind you once again, here are all the stimuli, and they vary as a function of their height and the position of where the line lies in the box, and they are binary. They're demarcated. There's a binary distinction between the two sets of stimuli. Right. So now, individual differences display the behavior, and through inference about the parameters, boop, 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 provide information that can help formulate more constrained models about the variation in category learning in this data set. Right. Uh-oh. I'm getting a phone call. One sec. Hey, hon.
You streaming?
I'll be streaming.
Okay, well, good night.
Wait, let me. Stream. Hello, stream. Hey, chat. Apologies. I had to step out for a moment to say goodnight to my partner, who is currently away. So I'm obviously living like an animal when she's not here. And mostly that means that I sit in front of my computer for an additional 2 to 3 hours per day, which is nice, depending on who you ask. But anyway, all right. So, getting back to it then. One worthwhile model assumes that there are 3 groups of subjects. Right, so we're talking about being able to better capture the variability within the model based on the posterior distribution, based on the joint posterior distribution that we observed here. How could we better account for or describe some of the variability occurring here in this plot? This might be insightful to the underlying psychology, as it says here. So it might be the case that there are 3 groups. This model is based on the insight, based on the 3 types of behavior that we talked about actually last time when we answered the exercise question, the final exercise question for the individual differences section. In the first group, subject 31 seems to categorize each stimulus roughly equally. This is consistent with guessing behavior. So we have guessing behavior. A contaminant, right, as we were saying, right? So it'd be interesting or important to control or account for guessing behavior. These subjects, posterior distributions with low generalization values and large uncertainty about their attentional values. You see there? They're all over the place. We don't know what they want. Let's see, this makes sense since low values of generalization lead to high similarity between all stimuli and near equal sum similarity. Something that I was looking for earlier. Low generalization lead to high similarity. A much simpler way to account for behavior of subjects like 31 is not to use a generalized context model to account for the behavior at all, but to separate a contaminant model that just sets their response probability to 1/2. The groups of subject represented by subject 3 and 33, meanwhile, show a more thoughtful categorization of behavior, but have different patterns of responding. Here, so it's just telling us which stimuli are associated with each of the categories, which we saw above, and subject 3 makes choices. Almost all their errors are on 4 or 5. And we saw that makes sense because it seemed like across the sample, people tended to make errors on stimuli 4 and 5, those 2 in the middle stimuli. We can look at the graph here. These 2. And that's consistent with the weighting on the attention parameter here, because these 2 stimuli would look fairly similar to one another if one was only attending to the lines and not the heights of the boxes, right? And then you look at subject 33, who performs poorly on 2 and 7. This is consistent with a focus on the height, right? So one's focused on the lines and one's focused on the height. And we want to implement a graphical model. Note the posterior distribution generated at the group level and that 3-valued classification variable z is constructed, showing up in a group membership for each subject. Okay, so we're going to now incorporate this latent class or mixture structure so that we can predict the probability of any given subject belonging to one of these 3 classifications, or it might be 2. Based on what they said above, it might be the case that people who are responding, guessing, are just going to be assigned this 1/2. But I'm not sure if we incorporate that in the model. So before I go down and read the descriptions of this parameterization, I'm going to just go ahead and try to take a stab at it and look for if I can identify some of the new particulars that might help explain what's going on here. Okay. And the first thing I notice is I'm just going to try to look for differences in the model. I'm seeing these z's, right? Z's. Let's see, Z. Okay, so we have phi for G and phi for C. And what does that mean? Well, phi for G and C are uniformly distributed from 0 to 1. So each subject still gets a weight. And this is Z for a given subject, but C. So each subject has 2 Z's. A Z with a subscript G and a Z with a subscript C. So I think that one of these are supposed to identify contaminant subjects, and then the other is supposed to identify groupings. Let me scroll up here. Make sure. All right, so we just get 3 of these for each subject. But now we're modeling it such that there is a sigma. There's a sigma and a mu parameter for each of the weightings, though each of the groups for the weight have different average weightings. Right, so there's a distinction in mu. Where's this coming from? So this is just telling us, okay, each of the 2 groups are going to have different average weightings, which we assume are going to correspond with high weighting towards one stimuli, and then really low weighting, which would be selective attention towards another stimuli. And then this would represent the probability of being part of any group, which we specify uniform distribution. So it can be 0 to 1, and so 1 is going to be one group, 0 will be the other group. And this is going to specify the probability of being part of a contaminant category. And then the generalization parameter has a mu and sigma attached with it as well. Though notice we're not specifying a difference in generalization as a function of groups. There's only one underlying distribution for that. Okay. And these are Bernoulli by this probability, so the rate of being a part of one group or another. Gaussian here. Restricted range, because generalization can only be 1 to 5 or so. Restricted range for sigmas or for those distributions. So if you're a contaminant subject, z for the contaminant for a given subject is equal to 1, and then your r, your probability, is just equal to 1/2. So we just specify you're doing guessing behavior. Okay. So let's take a look how this pans out in the WinBugs. And then we're going to move over to stand, unless we can implement this in WinBugs, which I'm not really sure if we can. But so for each of the stimuli, we'll look at each of the subjects, and we'll give a subject for an item. It's going to binomially distributed with this rate for a given subject for a given item, and this amount of trials. And then we specify groupings now. So groups 1 to 3. We'll do some predictive checks for groups here. Pretty G. So whatever for each group, for each item, binomially distributed. And we're going to make R predict G, which is just going to be 1 for each group for each item. Okay. Now the decision probabilities, we'll have 1 for each item for each subject, where R, IK, and then this syntax is just describing the if 0 or if 1. So here, if 0 could equal to this times that, and then sum 1 if we're equal to 1. If it's equal to 1, use this times that. Then for one of the two groups, because in this G, we're only looking at the two groupings, right? And then the third one is just 0.5. So if it's part of the two groups, use the numerator and denominator descriptions or derivations. And this just is just applying the formula above here. Right? Now for subjects, parameters. Oh, nope. Sorry, too far. Now we have to specify what is numerator, what is denominator. And then the decision probabilities for the groupings for the joint items. So we need to specify for specific groupings, there's going to be item. Where is it? Here. We're specifying this. Right? Numerator and denominator. No, this is still looking at R. It's just setting it up for what goes inside here when we're looking at these. And then the specify similarities for each item, pair for each subject. And there's how we also, for each one, we have to make predictions, or we also make predictions for each of the groupings. And now the priors for the parameters. So for each subject, we'll have these normally distributed. And then for each grouping, we'll have these. And then the latent mixtures, so the things that give us the indicators, normally distributed uninformative priors for each subject. Then we're going to have fees. We'll have the prediction fee, zk plus 1. We add 1 because of how it parameterizes itself. It does 0, 1, but we want 1 and 2, right? I think that's what it. And then finally z is equal, if it's 0, make it this, plus 3 if it's equal to 1. Ooh, here we go. Now we have to mean generalizations, okay. Five times mu temp. Right, so we'll get a value, the beta distribution, and then we just take the distribution and we make it 5. I think that's what that's saying. And then for W temp, it's also beta distribution. So mu weight, this is the mu generalization, mu weight, delta mu weight for the second group is equal to the minimum of the change from the mu weight. So whatever change we infer plus whatever mu we infer, that's going to give us the value here for mu of the second group, because what's not in the first group is in the second group. And then this is the generalizations for sigmas, right? So specify sigma, and then standard deviation for attention. I see mean generalization, mean weight. So this is mean for the generalization parameter. I see this is mean for the attention parameter. And then we specify sigma and standard deviation. And lastly, then we need to specify the lambdas, because lambda is what gets used in our formulas up here in the priors, right? Right, we have to use precision. So that was the reparameterization down there. Where else did they get used? Just there. Okay. So let's see if the results bear themselves out in the JAG code, which might not be there. Ooh. Yep, it's not here though. Interesting. One thing I just noticed, lambdas get used above here too for inference of the parameters, and these are predictives for the groups. I see. Yeah, it doesn't seem like there's a model here in the applied Bayesian analysis code that you download from the website. It doesn't have a model for doing the calculations in R. But do not worry. because we have some stand code. Let's see how it looks. Parameters, transformed parameters, mu, w, sigma. LP. I don't know what this is. Generalization. Min. I'm curious, when do we use fmin and fmax? Which just stand for getting the minimum and the maximum to that. And calculate similarity. So this is the groupings. LP parts. Is that just what we call it? Yeah, it's just the name we use. Log 1 min. Probability C is log G is equal to the pro. This last Z we get is what we want. Oops. I'm gonna watch these parameters. Over gonna blast off. Pew. Here's all the initializations. It's the absolute value. R norms, number of subjects. C. Ooh, divergent transitions. Uh-oh. Too low. Let's double the amount. So there I got indication of divergent transitions, which indicate that the Monte Carlo or the Hamiltonian simulation, the sleds are like not aligned to the, how does it work? Essentially means that the momentum calculated or estimated momentum in how the sampler is fielding or sampling across the parameter space, the momentum was off, or from what transitions were predicted. They were like not tight enough predictions. And this is something that's spoken about if you read a little bit about Hamiltonian Monte Carlo procedures. This is part of the algorithm, or one of the dangers of the algorithm are these divergence transitions. Additionally, it looks like there were other, or in part because of this potentially, is that we have large R hats, which is the within and between variance for our chains. We only have two chains here. And then that bleeds into, once again, having low effective sample sizes, which means our sampling is far too dependent on one another. And now we're still sampling here, but it looks like we'll finish in a second and we'll see if increasing the number of iterations and increasing the burn-in period helped with our models, the issues that we were having with the model originally. Doesn't look like it. We have 306 divergent transitions now. Have to increase to like 2,000 maybe. I just want to get one good one. And I'll go and read the book right now, so. What was 2,500 divided by 2? I don't know. Off the top of my head. Okay. We'll try this again. Okay, well, that's going. Let's take a look. So we get a couple plots here. Plot 1 before reading is the probability assignment of each of the subjects. So for a given subject, what is the probability that they were assigned to each of the categories, right? Subject 1 had a highest probability of being a contaminant subject, for example. And then, in fact, the probability of being a contaminant subject for the first, looks like 5 or so subjects was highest, and then sharply decreased. And we see they're on subject 6, and then it looks like there the probability of being part of the second pool of subjects that attend to the position is high. And then we have this smaller group of people who are attending to the height. So most people are attending to the position of the line. Then some people are attending to the height, and though some people are just guessing. It's likely that they're guessing. That's what I'd infer from this membership probability here. Hmm. Oh, that moves nice. Oh. Mm. Some results are not trustworthy, is what I'm getting at. Some results are less trustworthy than others. That's what we're getting. Baseline. This is the generalization parameters for each of the subjects. Here then is the weightings for each of the subjects. Here is the average generalization. Here is the average weighting for each of the two groups, group 2 and group 1. And then here's the variance surrounding each of the two groups, with there being more, this is the variance for generalization, and this is the variance in weight. Cool. And then we have the predicted groupings, predicted generalizations, and then we have just predictions for each subject's. Predictions for each subject for each item. And this is a pretty long list, it looks like. So if I wanted to get I'm just trying to see a little more here. Okay. So here for each of the subjects, 2 and 3. Oh, no, it's not for each of the subjects. Sorry, G stands for group. So this is each of the predicted groupings for each of the items. It makes sense that all these are contaminant subjects. So let's see, pretty Y, G. matrix 3. So this is each of the stimuli. This is the predicted counts. For each of the items, for each of the groups. Let me see what binomial RNG is. Stan. Generates a binomial variable with n trials. Right, so it's just generating a probability distribution with the posterior, with the specified posterior. So we're just getting the number of counts for A for each of the groups. So we'd assume there'd actually be one group that had higher values of A. So the first group's values of A. Second group's values of A. And the third group, which has this in the middle because they're guessing. It's like a 50-50. And then this is Z for each of the Ks, right? So every subject then was characterized into being one of the two groups. So some specified probability of being part of the two groups. But people like 31, looks like they just range over the entire distribution. If Z control is equal to 0, so they are not part of the control group, then G plus 1 plus 3 if G is equal to 1. So whatever group you're in, plus 4. So encoded in all these Z's then are the 3's, I think there's 3 groupings encoded in the Z's here. And that's how they extract this. So if we take a look at down here, code, right there, extracting the Z's. So let's take a look. What's Z look like? It's big, but Z is just this big. Oh, all the iterations are run that way. Okay. Z is each iteration probability of being part of 1, 2, or 3. And then pretty G print all of them. Is all of the predictions. Nice. All the predictions for each subject or for each sample. Now we just create 3 boxes, and then for each of the z's, we'll take give me the sum over the length for each of the subjects. So then for Z1, for example, we have the probability of each of the subjects belonging to the first category, and etc. So Z2, probability of each of the subjects belonging to the second, and then. So you can see here, if you looked, subject 1 is most likely in the second. I'm going to guess and say this is the contaminant one because we have a lot of zeros. And yeah, group 3 is the contaminant subjects. And then we just order them for the sake of the graph. And we don't want the window. We plot it. And here is first group, second group, third group, contaminant. Yep. And then we have some way to identify them. And that looks pretty. Mm-hmm. Okay, and now we're looking at the next one. And so these guys, there's posterior mass demonstrating that they could be part of many, either group. But part of that, recall, is because they're guessing. So people who are high in this have this sort of influx. However, people who are clearly a part of one of the groups seem to be mixed well here. 0 probability. And these tail subjects are... Okay. So then we look at the posterior predictive analysis. So these are the prediges. Each paranole corresponds to a group with the squares showing the predictive distributions of the model. Thick lines show average categorization for subjects classified as belonging to the group and as determined from the mode of their posterior group membership. So let's take a look. So across each of the 8 stimuli, we see that there's this average sort of in-between categorization of each of the stimuli. So most of the weighting in terms of the probability posterior distributions for counts of being classified as A are in the middle. However, if we took a look at the next one, and then the gray lines are individual subjects. If we took a look at the attending to the position, we see that we have this sort of pattern where the first couple stimuli are correctly identified, the last couple stimuli are correctly identified, and then these people tend to mix up 4 or 5, like we saw with the, I believe it was subject 3 or something above. Subject 3. So this underlying average stereotypical pattern of categorization. And then we also saw this pattern of categorization where people are tending to the height. So far more variable in terms of the response. Oh, well, not necessarily variable, but doesn't match that stereotypical sort of generalized pattern that we have been identifying across the group average, right? So this is like the group average sort of pattern as well. Because people mostly attended to the position, right? And that makes sense. See why this so heavily dominated the averages that we saw in the distributions of attending this predictions for categorizing as A we saw earlier. Though some people don't. And this is the pattern of responses for people who attend to height. And it seems to be well described in the posterior, see? So average, and then most of it's there, most there, weight's there, weight's there. The weight sort of matches where the average categorization was for this pattern of responses for this group. So the analysis presented the focus on the inferred group membership and the posterior distribution of each group. These might be two of the most important inferences, but they are not the only available or useful ones. Extend the analysis by considering the posterior distribution of the inferred proportion of contaminant subjects and the difference in group mean. Attention? Okay. So we can go and extract those parameters and we can take a look at them. So it wants us to look at phi C. Wants us to take a look at the phi C, if you know what I mean. It's a poop joke. And then it wants to look at the mean diff, which is delta. You know, and this might actually be a cool time to use this. I'm actually going to get something. I'm going to try it. In my Bayesian Statistics Students Guide, I'm currently on the STAN chapter. And within this chapter, there's actually a recommendation to try to use this Shiny app for model diagnostics and visualization. So I'm just going to look at the code and see if we can just try to implement that right now. See what happens. And here we go. It launches it as an HTML in your web browser. And let's diagnose. Ah, I see. So if you look here, boy, we got trapped at some areas. It looks like there's not This is not a good mixing. I would not trust these results based on these mixing. And that's for the delta parameter. But that's one of the parameters we want to look at. Oh no. Well, here's a histogram for the delta parameters. Certainly is a difference. Okay. And phi C looks better. But let's take a look at something like the weighting for each of the groups. Alright. But this kind of mixing makes sense using 0 and 1, right? So here's delta. And this is equal to the average difference between the two group means, right? So there's a large difference between the mean weighting between the two stimuli. Attention towards stimuli. But let's look at this. So this is the contaminant probability, right? So looks like highly autocorrelative in the second sample. There's some autocorrelation issues. Can we look at all the C's? Oh, don't want to look at all the C's. Posterior predictive checks. This is cool. See if I just wanted to look at delta. Scatter plots. Estimates. 85% confidence intervals. 80% credible intervals here. For each. Here's the summary statistics. This is really cool. Explore. Oh, you can look at bivariate distributions. So I can look at delta. Oh, I can look at delta and phi. So no relationship here. And trivariate too. It's cool. We can go delta phi For example, I could look at the probability of being part of a grouping and some of the weighting, or someone's prediction, generalization, and their weight. This is for one subject, right? Sorry, pretty weight doesn't have to do with the subject. Let's use Z. That's cool. So it's not likely they're part of the contaminant group. And then this is weightings. Or just disperse apart in the parameter space, but dense around the value. This is cool. Okay. Very interesting and cool tool. And it looks like it's going to help us answer some of these questions that posterior distribution of the inferred proportion of contaminant subjects. So how many contaminant subjects are there? The proportion of contaminant subjects represented by, if you see, let's look at the histogram. Average is 6% of the, with a high of 26%. So we had an average 6% of contaminant subjects in the, right, but most of it is around one below, like 6%, yeah. 6 to 10%, looks like. Median of mean. That is not a nice, like this. Mean. And then we have zeros. So it contains 0. So there's a possibility that we had no contaminant subjects. 10%. Or 1%. With upward high of 3%. And this is a reliable estimate and effect size of that. Okay. Cool. And now the second statistic it wants us to look at is the differences in group mean attention, delta. So delta then represents the differences in group mean attention. So this is someone minus someone. And it looks like, if we're thinking about hypothesis testing here, there is certainly a difference. And this difference is large. But the estimate looks unreliable, right? Mm-hmm. One thing might be cool. We can just look at the mean of both. Right. It's a multi-view. And let's take a look at the mean of group 1. Bivariate. And we'll look at the mean of group 2. Or mean weight's high over here. Over here. So what does it mean to have a difference between the weightings? What is the psychological interpretation of that? It's the residual attention. It's the attention given to is like the average attention given to a opposing selective or an opposing feature of the stimuli. What's delta calculated in here? Oh, okay. Delta at 0.5 would indicate that there would be, in terms of the ratio or odds between attentional weight towards one parameter or another, it would be equal. But because in the histogram here, we see the value is higher, that delta then indicates that there is across a sample, a preference towards one attentional weight over the other. And in this case, we know from looking at the data that that is people's attending towards the position rather than attending to the height. So that's what delta is capturing here, this attendance towards position rather than height. It's the dominant categorization of stimuli. I think that's the psychological interpretation. Construct the posterior distribution for the probability that a subject is in the attend group rather than the attend height group. So rather than looking at the weight or the dominant weighting, this is asking for a ratio. Mm-hmm. You can do posterior predictive checks in here. That's cool. So I don't think I can just estimate. Okay, so I want Fiji, right? Construct a posterior distribution for the probability that a subject is in the position rather than the intended. So we would have to use the average weightings, right? And we do some odds. So we'd scale. Let me just think about this. Here's Fiji. Probability is high. So the probability that people are in the 10 position group is higher here. But we want to know the proportion, right? So we want to know group membership. Or can we identify group membership? So let's think about it. Fiji is the probability of being a part of one group. It's the base probability of being a part of a group. So we need Fiji over or under. Has to represent some odds. I think it's just okay. Oof. Right, I can't do that while this is open. Save and close. Okay. I couldn't execute code while that was open. So Fiji. The odds are equal to. Cool. think maybe I have some code docs. I think from one of my lectures. Set the log risk ratio. The log odds ratio. It's Fiji. Odds Fiji. But what parameter represents being a part of the other group? That's what I need. Hmm. That's not it. Oh, let's try this. I think this is it. Hmm. Man, I could have sworn this was right. Maybe I can do that. I got nothing. Got the 50-50. I took the probability. I took the probability weighting for each of the two groups, predicted probability weighting for each of the two groups, try to create an odds ratio between them. That's not it. Alas, I'm out of time for the night. But essentially, we're trying to create some ratio or some assessment of the odds that would give me an odd of someone attending the one group rather than the other. Construct that subject is in the. So I'm looking at what is the odds of a subject attending to one attend position rather than attending to height. And it's not just the G parameter, which represents the probability of being a part of the height group is higher, or the line group is higher. Line group, right? Line group, yeah. Alas, we gave it a good show. That's going to be it for tonight, folks. Thanks for sticking around. I hope you enjoyed my little exploration of the Stan Shiny package that allows you to do diagnostic sort of check and post-predictive checks within the graphical interface, and gives you access to all these neat charts that lets you look at the chains, and if you're having issues of divergence like I was talking about earlier, you can diagnose those problems within there. You can also look at joint posterior distributions across your variables, which is nice as well. So that's going to be it for tonight. We went long, the whole hour 30 looks like, but thanks for sticking around. I look forward to starting the next chapter tomorrow, and we'll give it a good show again. I'm going to think a little bit more about the question and see if I can get some insight from some colleagues. Maybe they'll be able to help me deduce a answer, and if I do find a solution, I'll be sure to check back in with you guys. Thanks. You guys have a great night.